Let's continue our videos with this practice question. So this one is probably it's better if you read it to yourself. I'm just gonna underline everything that is given. So push the pause button, read the question, and then we're gonna start solving it. So information that is given: the actor is 65 kilogram, the sandbox is 130 kilogram, the rope or the cable that he is pulling on when he is swinging or holding to is 3 meters, and when he is all the way at the bottom, we don't want the sandbox to move. So that means the tension that he is going to be having here in the sandbox should be equal to the tension that is holding the sandbox. So the tension that he is applying on the rope when he swings should be equal to the sandbox tension. And also, if the sandbox is the capital M and the actor is the lowercase m, then I have the forces acting here is mg and the tension, and here is mg as well for the sandbox. And I also have centripetal acceleration because he is moving in a circular motion. So if I write my the second Newton's law equations for each mass, for the actor and for the sandbox, I have the tension minus mg is equal to 0 because the sandbox is not moving up or down, or there's no acceleration. Or I can just say that the tension is equal to mg. So the tension is equal to mg. And for the actor, I have the tension minus mg, and he has acceleration, centripetal acceleration, so that is mac. And instead of mac, I can say v squared over r. R is the length of the rope, so I'm going to call this one is L. So right there is given 3 meters L. So instead of r, I can plug in L. And if I solve this equation is already solved for t, I'm going to solve the second equation for t, or just move mg to the other side. So if I move mg to the other side, I have mg plus mac. Now if I set these two guys equal to each other, I have mg is equal to mg plus mv squared over L. And what I don't know here in this equation is v. I need to find the velocity of the actor all the way at the bottom of his swing. So I'm going to draw another picture right here to work out my velocity part. So if he is at certain height h, and by the time he gets to the bottom, his potential energy is going to turn to the kinetic energy, which is 1/2 mv squared. So this mv squared could be replaced with this mv squared. So I'm going to use kinetic and potential energy to calculate what I need to replace this mv squared, because I do not know the velocity. So the potential energy is equal to mgh, and here is the angle. If I make this triangle right here, then this becomes L cosine, because the length of the rope or the cable is L. So this is L cosine theta, and the bottom is L sine theta, but I don't need the L sine theta. And the whole length, the whole height right here is L. So H is equal to L minus L cosine theta, or H is equal to L 1 minus cosine theta. So for the potential energy, I have mg. Instead of H, I have L 1 minus cosine theta, and equals to 1/2 mv squared. So mv squared, the part that I need to replace in the other equation, is equal to 2 mgl 1 minus cosine theta. I'm gonna go back to my problem and I will say that mg minus mg is equal to, instead of mv squared, I have 2 mgl 1 minus cosine theta and divide it all by L. And L can be cancelled. And every single one of them has a G, so every term has a G. I can cancel G as well. So what's left is M minus M is equal to 2M 1 minus cosine theta. I'm going to distribute it, and I have M minus M is equal to 2M minus 2M cosine theta. Then I have M minus 3M divided by negative 2M is equal to cosine theta. So theta is equal to arc cosine of, and here's the little trick. I can take this negative in front instead of keeping it there. And then I can place negative to the top. So I'm going to take the negative from the front and place it to the top, to the numerator. So that will give me 3M minus M over 2M. And my angle is going to be equal to, the mass of the actor is the lowercase m is 65. The mass of the sandbox is 130. So let's plug it in. And I get 60 degrees. So I figure out the maximum angle the actor can have with the vertical in order to swing all the way to the bottom and not to pull the sandbox up. So it would be safe for the actor. So that would be 60 degrees. So this angle is 60 degrees. Let's look at this question. Suppose that a 1800 kilogram car passes over a bump in a roadway that follows the arc of a circle with the radius 20.4 meters. What force does the road exert on the car as the car passes the highest point of the bump if the car travels at 8.94 meters per second? And what is the maximum speed that the car can have without losing contact with the road as it passes this highest point? So again, let's write all the forces acting on the car. So we have the mg, and we have the normal force from Newton's, and there is centripetal acceleration because the car is moving in circular motion over the bump. It's a part of the circle, the track that is moving on. So for the Newton's second law, I have the normal force minus mg is equal to negative mac because ac is downward. In other words, I have the normal force, let's write here, the normal force is equal to mg minus mac. So the car is going to be feeling lighter all the way on the top of this circle. And velocity is given. So the force that they're asking about is the normal force is equal to, the mass of the car is 1800 kilogram times 10, gives me 1000, minus 1800 times velocity squared. So that is 894 squared over the radius. They give you 20.4. So the normal force acting on the car at the highest point is equal to 70,1996 newtons. So instead of the weight, which is mg 18,000, the car only weighs 17,996. So that is for a part. But for the second part, they say the maximum speed that the car would not lose the control. So for the maximum speed, your normal force is going to be equal to 0, because if the car is losing control with contact with the road, with your normal force is going to be equal to 0. So what I have for B, the normal force is equal to 0 and equals to mg minus mac. That means mg must be equal to mac, or g must be equal to ac. In other words, g is equal to v squared over r, or v is equal to the square root of rg. And if I plug in my numbers, I have r is 20.4 times 10 gives me 204. So the maximum velocity at which car can drive is equal to the square root of 204, 14.3 meters per second. So that would be the maximum speed at which a car can go over the track, the highest point, and not lose control. Here's another problem that I want to solve with you in this video. I want you to pause it because it's a lot of time it will take me to read the whole question, and I'm limited to 30 minutes per question. So go ahead and pause the video so you can read it, and then when you're done reading, just unpause it and let's do the question together. So they asking you that if the spring with a spring constant that is given, compressed with a block M is given, and then after it is released, so it compressed a certain distance x that I don't tell you, and then after it is released, it will go through the area between A and B when there is friction, and they give you coefficient of friction, kinetic friction, because it's sliding in this case. And so when there's no sliding, there's static friction. When it's sliding, it's kinetic friction. And then it has to barely make it through the vertical circle of radius 1.5. So that means at point C, the normal force has to be equal to 0. So I'm gonna place the forces at point C on the block. So you're gonna have the normal force acting on the block. You're gonna have mg acting on the block. And you're going to have centripetal acceleration because it's going to be moving in a circular motion. So for the net force at point C, you have the normal force minus mg and equals to negative mac. Or the normal force has to be equal to 0 because they say it barely makes it. So the normal force is equal to 0. That means that acceleration has to be equal to g, centripetal acceleration, or v squared over r needs to be equal to g. So I'm gonna start with potential energy of the spring. When you compress the spring has potential energy of the spring, and that potential energy minus the work done by the area AB, where there is friction, or I can say the work done by the friction. So right here I'm gonna have friction, and the rest of the energy is gonna go to the kinetic energy, and that kinetic energy will turn into the potential gravitational energy at point C. So I will have potential gravitational energy at point C. So what I can say is 1/2 kx squared, that's the compression of the spring, minus mu times the normal force on AB, and the normal force on AB on the block is, so if this is the block, you have mg and you have the normal force, so the normal force would be equal to mg in this case, so mg, and the distance is d between A and B, and all that is equal to mg and potential energy, and the height that it will rise to is twice the radius of the loop. They asked me to solve for x, so now I'm going to times every single term. So there's 1 term, 2 terms, 3 terms. I times them all by 2, so I have kx squared minus time, oh, let's move mu to the other side and times it by 2. So I will have 2 mu mg distance AB plus mg, and I have to times it by 2, but there's already 2, so I'm just gonna make 4 plus 4 mgr, and I'm solving for x, so x is equal to the square root of So I plugged in all this, but I also see that every single term on the top has mg. So I'm going to take mg out. And what's left is, at the bottom is still k. And on the top I have 2 mu d ab and plus 4r. Now if I plug in my numbers, I will have, so I have 0.69 meters or 69 centimeters. So either answer is okay. So this is the compression you need barely for the block barely pass over point C. So it would have enough energy just to pass over C. So here's one more question I want to look with you in this video. And again, pause it, read the question, let's underline everything that is given, and then we're going to continue with the problem. So go ahead and pause it. So you see that there is a mass of 0.5 kilogram and the length of the string is 1.5 meters, the angle is 30 degrees, and it is revolving at some speed. We have to determine the speed when it is moving at this in this motion. So I'm going to write the forces that are given, or that are present. So the forces acting on the ball is the tension force, and then you have mg. The radius of the circle is, so if the string is L, then this part is L cosine theta, which I don't need, but the radius is L sine theta, because that's the radius at which circular motion is happening. But also the tension has horizontal vertical components. So horizontal component is going to be T sine theta, and vertical component is going to be T cosine theta, because theta is the top angle right there. And let me rewrite what R is equal to. R is equal to L sine theta, and this is your R. So this would be your R, and that is L sine theta. And here is the vertical component of the tension, T cosine theta. So because it's circular motion, there's still going to be a centripetal acceleration. So here I have it in green, centripetal acceleration toward the center, and horizontal component is right here, T sine. So now I'm going to do the Newton's law for vertical and horizontal motion. For vertical motion, I have up direction T cosine theta and negative mg, and there is no acceleration vertically, so that equals to 0. And then I have T sine theta, and there's no more horizontal forces. That means that the only force is equal to MAC. Then I'm going to rewrite these two equations. I'm going to rewrite the top one on the bottom, the top on the bottom, and the bottom on the top. So I have T sine theta is equal to MAC, and T cosine theta is equal to mg. And I did this intentionally, wrote them the way I wrote them, because I'm going to use that trick that I showed you in a few videos already. I'm going to divide the left and right side of both equations so I can cancel t's. So t's will be canceled, and I have tangent theta, sine over cosine is tangent, and also I can cancel the m's, and I have AC over G. In other words, tangent theta is equal to V squared over R, that's acceleration centripetal, and divided by G. But your R is equal to L sine theta. So instead of R, I'm going to plug in L sine theta. And I have tangent theta times, instead of R, I have L sine theta, and times G is equal to V squared. So V is equal to the square root of LG sine theta tangent theta, and equals to 2.08 meters per second if you plug in all the information that is given. So that was for part A. For part B, they say if instead the ball is revolved at the speed of 4 meters per second, so it's not 2.08 meters per second as we calculated. Now it is 4 meters per second, so the angle is not going to be 30 degrees anymore, the one that I gave you earlier. It's going to be a different degree angle. So what angle does it make with the vertical? So now we have to figure out that angle with the vertical. So I'm going to erase this work and rewrite it again. So I erased the work where we found the velocity 2.8 meters per second, and I just rewrote this equation as AC is equal to G times tangent theta, and that is equal to GR tangent theta, and that gives me GL sine theta instead of R, and tangent theta. So this part is instead of R, so that is your R. So here is tangent in my equation, and I know that tangent is equal to sine over cosine. So if I plug in instead of tangent sine over cosine, so I'm going to erase tangent and plug in sine over cosine theta, I'm going to have a different equation. My new equation is going to look like V squared is equal to LG, and then sine times sine gives me sine squared theta over cosine theta, times both sides by cosine, and I have V squared cosine theta is equal to LG sine theta squared. Now I'm going to use another trick. I'm going to say sine squared theta plus cosine squared theta is equal to 1. And I know you have seen these type of equations before in your trigonometry or pre-calculus class. So now I'm going to replace sine squared theta with 1 minus cosine squared theta. So now I'm going to have, instead of this equation, I'm going to have V squared cosine theta is equal to LG, and instead of sine squared, I have 1 minus cosine squared. 1 minus cosine squared theta distributed, and I will have V squared cosine theta is equal to LG minus LG cosine squared theta. Now L is 1.5, so going back right here, and velocity is 4 meters. For B, they have velocity of 4 meters per second. So I have 16, because it's 4 squared, cosine theta equals to LG, gives me 15, minus LG, which is again 15, cosine squared theta. Let's move all of them to one side. So what I have is 15 cosine squared theta plus 16 cosine theta minus 15 is equal to 0. And I want you to look what this looks like. If I replace cosine with x squared and x, what I get is 15x plus 16x minus 15 is equal to 0. I get quadratic equation. So now if I solve for x, I have the opposite of b plus minus quadratic equation. B squared minus 4 times a times c. C is negative 15, so it will change that sign to positive. And divided by 2 times a. So x is equal to, you will get two answers. One is 0.6 and the other one is negative 1.67. But your x is actually not x, it is cosine theta, because I replaced cosine theta with x, so my cosine theta is x. And your cosine cannot be greater than 1, because cosine is the adjacent over the hypotenuse, and adjacent side cannot be over hypotenuse greater than 1, so that is not an answer. So I have to figure out what theta is equal to. So that is arc cosine, or in your calculator it looks like this, of 0.6, and that will give me 53, make sure it's in degrees, 0.13 degrees. So in order for the mass or the ball be rotating at 4 meters per second, it will have to be at an angle of 53.13 degrees. And now let's look at the C part. The C, they say if the cord can only withstand a maximum tension of 9.8 newtons, what is the highest speed at which the ball can move? And just to tell you the calculations that we just figured out and calculated this 53.13 degrees, you will never see this on AP exam, so calculated, such difficult calculations. So this is not something is going to be given on AP exam, but at the university definitely you're going to have something like this to work with. Okay, so for C, they give you the tension. So if they give you the tension, if I look right here, your T cosine is equal to mg, or I can look at it right here. Your T cosine is equal to mg. So T cosine theta is equal to mg. If they give you tension, which is 9.8, then your cosine theta is equal to mg divided by tension. That is m 9.8. I'm going to plug in 9.8 in this case, not 10, because this is also 9.8. These guys cancel. And what your cosine theta is equal to, the mass, which is 0.5. And cosine is equal to 1/2, or you can do it through the calculator, is 60 degrees. So theta would be 60 degrees. Now, since I know theta is 60 degrees, I can use the second equation, which is T sine theta is equal to MAC, which is m times v squared over r, but your r is L sine theta, so right there where we figure out what the radius is equal to. So we have mv squared over r, which is L sine theta. I'm going to times both sides of this equation, so this is equal to this, times both sides by L sine, so we don't have a fraction. So I have T times L, sine times sine gives me sine squared theta, and equals to mv squared. So if I'm looking for v, that's the maximum velocity you're looking for. It's the square root of TL over m sine squared theta. And you can take the square root of the sine theta squared, so that is giving you sine outside of the square root, and you have TL over the mass. So you have the sine of 60 degrees, and make sure that your calculator is in degrees, and T is 9.8, that's what they give you in C. So you see in C they give you 9.8, and L is 1.5, and the mass is 0.5. Now if I plug in my numbers, I get my velocity is equal to 4.7 meters per second. And that will conclude our problem solving for this video, and I will see you in the next video. The other video is going to be more about gravitational potential energy, different one, not the one that you're used to, and that will be about the video about the gravitational potential energy when the objects are not on the planet, when they go farther away from the planet, and the escape velocity. So that's going to be the next video about, and thank you for watching. See you in the next video.